Sorry, my cat's loud.
Just a quick reminder of what's coming up. I have the calendar up from Canvas. And so today is the 9th. There is an online midterm exam, which will be open till 11. I need to extend your time. I haven't done that. So let me do that once we're done.
Is it just on the lab that's not on any?
Yeah, it just labs 1 through 5.
Okay, is it going to be set up similar? Like it's going to have like the videos and we answer questions, or?
Yeah, there'll be, let me think here. Mostly questions, all multiple choice. I don't believe there's anything to write in. There might be a video or two, but other than that, I gave 2 hours regular time. But if you think you need more than that, what do you think?
Ooh, I don't know.
Well, I'll go ahead and go in there and let me make a note to self here to increase the time. So, okay. All right, so coming up after that, we have on the 24th, exam number 3, and we'll do the same thing we did before, okay? So,
And the exam is just on the lecture material, right?
that is correct.
Okay, gotcha.
Okay, now this is the page that we ended up, we were doing Lewis dot structures. Okay, where the basically the steps were 1, look at all the atoms that you have. You've given the central atom, telling you that that's the central atom and then everything else is bonded around it. And then we go to the periodic table, find the atoms, all atoms, determine how many valence electrons each one brings into the compound, and we add them up. So in the case of water, H2O, we have 2 hydrogens, each with 1 valence electron, hence 2 times 1. And then oxygen being in group 6 brings in 6 valence electrons. So we have a total of 8 valence electrons to work with. And with those, we're going to build the structure. And also to keep in mind is that we're striving for the octet, with the exception of hydrogen, because hydrogen's rule is a duet and not a octet. So once you put 2 hydrogens around, 2 electrons around hydrogen, then that's happy, then you got to put them someplace else. Since oxygen is the central atom, you can very quickly make a bond between the 2 hydrogens and the central atom here, oxygen, and that's denoted by the solid line. That solid line represents 2 electrons. And so very quickly that you can see you took care of 8 valence electrons. Now what I like to do, and it's just a personal choice, once I calculate the number of total valence electrons, 1, you should always have a number at the end that is divisible by 2. So when I calculate 8, I divide by 2, and that tells me I have 4 pairs of electrons to work with. And so I can very quickly just draw a line, like a hyphen, and that represents a pair of valence electrons. You don't have to do that. You can, if you're happy with putting 2 dots, that's fine. So we can, as I was stating, by bonding the 2 hydrogens, that takes care of 2 pairs of 4 valence electrons. And then obviously we can't put any more because that leaves us with 4 pairs to work with. 2 pairs to work with, 4 electrons to work with. We can't put them on the hydrogen, and the only logical place for them to be will be on the oxygen itself. And so that's what those 2 dots represent. If we go back and check to make sure you still have 8 valence electrons total. And if we count around just oxygen itself, hold on 1 second. And if we just look at just oxygen itself, we'll see there's 8 around it. 4 of them are being shared with the hydrogen. those 4 that are shared are counted toward the hydrogen and the oxygen. And so we got a total of 8 valence electrons around oxygen, which fulfills the octet. We still have a total of 8 valence electrons, and that's what we calculated. So we can't add or subtract any. We got to work with what we have. And so this structure is is what we come up with. So once we do that, we need some more information to determine the geometry. And so we use the general formula ABE. A is always the central atom. And so you're always going to have one A, regardless of what the central atom is. So in this case, oxygen is represented by A. B is whatever is bonded to the central atom. They can be the same or they can be different. In this case with water, they're the same. So we got 2 of them. So that 2 is a subscript 2. I can't do the subscript. And then E, sometimes you have E, sometimes you don't. In this case, we do have E, which represents the number of lone pair or not bonded electrons to the central atom. We have 2 of them here. We have 2 pair. So E becomes E2, subscript 2. Okay, that tells us the general formula for this molecule that we come up with respect to water. With that information, then we go to the shapes table, which is a very important table that we utilize quite a bit. And we look at the first column and we look for AB2E2. And that happens to be the bottom one. Let me zoom it up a little bit. AB2E2. So that tells us that is the structure, the next column, and the spheres represent the atoms. The center one is A, in this case oxygen, and then the other 2 that are bonded to the central atom, here in this case with water, represent hydrogen. There's the lone pairs. That oval shape is just to demonstrate that those electrons take up a lot of space, and hence what happens, that bond angle between B gets squished in. So normally our reference point is the tetrahedral shape up here, and that is when the central atom is bonded with 4 atoms around it. And that is the optimum, which is what we find a lot out in nature, the optimum bond angle between whatever is bonded to the central atom, and that is 109.5. But because those lone pairs occupy a lot of space, and water has 2 lone pairs, so they occupy quite a bit of space, that angle between the 2 hydrogens gets squished in. And so our bond angle becomes much less than 190.5. And that particular configuration has a name for water, and the name of that shape is bent. Okay, and so the general formula gives us AB2E2, which comes from the Lewis-Knot structure. There's the geometry. The name of that is bent, and that bond angle is less than 109.5. Okay, so that's how we use the shapes table to tell us what the geometry is of the molecule, of the formula that we come up in the 3-dimensional mode. Excuse me. So going back. So that's the formula. That's what we have. All right. So we went ahead and tried these, and I gave you guys structures, the formula that we come up with, and practice them. Hopefully you can come up with that, but you can see here that the one that's 3 fluorides around it, 1 hydrogen, there's a lot of valence electrons there because there's 3 fluorides, there's 7 valence electrons per fluoride. So 7 times 3 is 21. Carbon brings in 4. Okay, so that's 25. And then hydrogen brings in 1, so that's 26 valence electrons to work with, or 13 pair. Okay, and then doing the same for ammonia, which is the one in the far right corner, you end up with a lone pair on the nitrogen, which is important information, but I'll get to that here in a second. Now, if we look at the bonds between the central atom and whatever else is bonded to that, we talk about the differences in electronegativity. We talked about that, electronegativity. And how's that come into play here is when there is a bond between two different atoms, the fact that they have different electronegativity results in that pair that's being shared to be shared unevenly. And so if we look between carbon and hydrogen, in this example, let me highlight it, between carbon and hydrogen, fluoride has a much higher electronegativity. Remember from the table, the fluoride is the one element that is the most electronegative. And the trend was from left to right and bottom to top, the electronegativity increases. And so we can see with fluoride being much more electronegative, that bond between carbon and fluoride will not be shared equally, but it will be shared unequally toward the fluoride. In fact, that occurs for all three bonds and all three directions. Now, the bond between the carbon and the hydrogen is one example where we treat it as equal sharing, because the electronegativity of hydrogen and carbon is essentially the same. And so there is no what we call a dipole. It does not generate a positive end and a negative end. Now, it's not generating a full positive or a full negative like the case with ionic compounds where you have sodium chloride. Sodium has a full positive charge and the chloride has a full negative charge. It's creating a partial negative and a partial positive. And so because the fluorides are a lot more electronegative, pulling the electron density away from the carbon, it kind of makes the carbon kind of deficient in the electron density. So it results in a partial positive charge in the central atom and a partial negative toward the fluoride because of the differences in electronegativity. That results in what we call a polar bond, okay? Now, carbon-hydrogen, because there's no difference in electronegativity, it results in what's called a non-polar bond because there's no net negative or net positive. The share is equal. Now, because the general trend is this, when you have a molecule that exhibits all non-polar bonds, okay, then the overall polarity of the molecule will be nonpolar. And so in this example, if those fluorides were replaced with nothing but hydrogen all the way around, so you have 4 hydrogens, then you have 4 nonpolar bonds resulting in a nonpolar molecule. But we don't have that here. We have 3 bonds that are polar and 1 bond that is nonpolar. That makes this compound a polar molecule, okay? Now, if we look at carbon dioxide, which is in the top right corner, going through the same analysis, we see a bond between carbon and oxygen. Now, if we look at the electronegativity on the periodic table, their position on the periodic table, we'll find that oxygen is much closer to fluoride. Therefore, the electronegativity of oxygen is greater than carbon, just like the fluoride was. And so it creates a polar bond in the direction toward the oxygen. And it occurs from right to left, but it also occurs on the other bond, okay, in the opposite direction. So these arrows are pulling in opposite direction. And because of that, what happens is the polarity on the right side cancels the polarity on the left side. So the net result for carbon dioxide, even though they have polar bonds, is because the polar bonds cancel out, then carbon dioxide is a nonpolar molecule, okay? So the rule of thumb is this. like I said, with nonpolar bonds, if they're all nonpolar, then you have a nonpolar molecule. With respect to polar bonds, if the polar bonds do not cancel out like carbon dioxide, then you have a polar molecule. If they do cancel out like carbon dioxide, then you have a nonpolar molecule. We're going to get that, use this information further down the road to determine properties of these molecules, such as solubility, such as boiling point, when we want to compare two different molecules and say which one is a lot more polar and so on and so forth. So we need to grasp how to determine whether a molecule is polar or not, because down the road, we're going to use that information to, one, determine what type of interactions these molecules have with each other, which then determines what type of properties they have with each other. Now, in the case when you write a Lewis dot structure and you have a lone pair on the central atom, without any doubt, without any question, you always have a polar molecule, okay? Always have a polar molecule. Let me back up for a second. Going back to the floral, it's called a floral hydrocarbon on the left-hand side. If I were to replace that hydrogen with another fluoride, okay, and I'm gonna see if I can put one in there just for demonstration purposes. Replace that hydrogen with another fluoride, something like that. Or you get the gist of it, right? Now, I have 4 polar bonds, and you would think, oh, okay, I got 4 polar bonds, I'm gonna have a polar molecule. But because of the geometry of the bonds, because that eventually is tetrahedral, and let me direct you back to the shapes table. Here's tetrahedral, okay? And imagine the carbon in the center, and we have 4 fluorides all the way around. You would guess that conclude or say, okay, 4 polar bonds, I got a polar molecule. But in this configuration, in the tetrahedral, when all of the species are the same element, other than hydrogen, you get a polar bond. But in this configuration, all 4 polar bonds cancel each other out. So even though you got 4 polar bonds, dispositioned like carbon dioxide in the tetrahedral, they cancel out, so you end up with a nonpolar molecule. Okay. But in here, in this case, no, that's not the case, because we have 1 nonpolar molecule and 3 polar molecules. Now, with respect to the lone pair, as I was mentioning, oh, where'd it go? When you have a lone pair in the central atom, either 1 or 2, always without question, you got a polar bond, okay? If we look at the next the example on the left corner, we have the hydrogen cyanide, which again, if you look at each bond, between the carbon and nitrogen, 2 different elements, therefore we have a polar bond. It's not carbon hydrogen, but it's carbon nitrogen. The nitrogen is a lot more polar, I shouldn't say polar, it has a higher electronegativity than carbon, therefore it would pull those electrons in that triple bond toward itself. And so we create a polar bond. With respect to the carbon hydrogen, as I stated, we don't have a polar bond there. It's 0 because the electronegativity between carbon and hydrogen is the same, okay? That's why, for example, fats and oils and vegetable oils, most of them are carbon hydrogen bonds. And because of that nonpolar bond, you have a nonpolar molecule. We all know that oil, which is nonpolar, will not dissolve with water, which is very polar. They don't mix at all. They're not miscible in each other. Okay, so HCN will be a polar molecule. 1 polar bond, 1 nonpolar bond. The net result is polar bond. All right, so we went through this, and then let me clear this. Okay, so I took one of those four and I went through it in detail. And we picked the HCN. And I did this for a reason, because it demonstrates how you make, when you fulfill the octet, you put the electrons around all the atoms, and then once you calculate the valence electrons, you put them all around the atoms wherever you can find a place to put them. And then you go back and check the octet and make sure that everybody's got 8 around it. Well, when you don't have enough valence electrons, like I said, you have just X amount. You can't just magically throw one in or take one out. You start creating double bonds and or triple bonds until such a point that the octet is fulfilled with all the atoms. So I took HCN, we added up all the valence electrons. Hydrogen brings in 1, carbon brings in 4, and nitrogen brings in 5, which is a total of 10 valence electrons to work with, or 5 pairs. Okay. The carbon is underscored, so that is the central atom. So the nitrogen and the hydrogen are bonded to the central atom. So I can very quickly draw that structure of H hyphen carbon hyphen nitrogen. That represents the bond between hydrogen and nitrogen to carbon. And that takes care of 2 pairs. So that gives me 3 pairs left to work with, and I got to put them on one of the atoms. Obviously, I cannot put them on hydrogen because hydrogen now is full with its duet rule. So the only place I can put them is either on the carbon or the nitrogen. Which one you want to put them on, just put them in any atom you want, just don't violate the octet rule. All right, so by doing that, I have the 3 pair, and I can very quickly draw them around the nitrogen. So that's where those 3 lines represent the 3 pairs. So I double check to make sure I still have 5 pairs to work with. That sometimes when I start drawing, you might inadvertently lose one, or you inadvertently add another pair by mistake. So I go back and check, and I do in fact have 5 lines that represent 5 pairs of electrons, or 10 valence electrons. I go now and check the octet or the duet, depending on what the molecule is. And if I look at hydrogen, hydrogen is sharing that pair with carbon, so hydrogen is happy with its duet. And if I look at nitrogen, nitrogen as written has 8 electrons around it. 3 of them are not bonded, and 1 is shared with the carbon. So hydrogen is doing okay. It's happy with the octet. The only problem child is carbon, because if you look at carbon now, it only has 2 pair around it. Okay, so it's missing 2 more because it needs the octet. Now, since nitrogen has extra, I want to say extra electrons sitting on there doing nothing, we can borrow a pair or maybe 2 pair from the nitrogen and create a double bond or a triple bond until such a point that the octet is fulfilled. So by doing that, I create a triple bond between the carbon and the hydrogen, okay? And then I go back and check the octet to make sure that everybody's happy. Again, hydrogen's okay, no problem with hydrogen. It shares that electron there. The nitrogen, okay, it has 1 lone pair, and it has 3 bonded pair. So that's a total of 8 electrons. So the nitrogen is doing good. And then finally, we check the carbon, and that carbon has 1 pair shared with the hydrogen and 3 pairs shared with the nitrogen. So its octet is fulfilled. And so that's our general formula. And that's our formula that we come up with. And then we create or determine the general formula to figure out the configuration. we have A, and then we have B, and there's two moieties bonded around A nitrogen and a hydrogen. Again, remember B can be anything bonded around the central atom, and it can be the same or different. In this case, they're different, but there's two of them. There's no E here because there is no lone pair, unbonded pair on the carbon. So our general formula is AB2. So with that information, we go back to the shapes table and we look for AB2, and there it is, the first entry. The geometry is given there. And the shape, the name of the shape is called linear, and that bond angle between, in this case, nitrogen and hydrogen is 180 degrees. Okay. All right. Now, so far we've done neutral molecules, but we can do the same thing with polyatomic ions. You might say, okay, what polyatomic ions? Well, these are the ones from the periodic table on the left-hand corner, where we have the polyatomic ions, ammonium, acetate, hydroxide, cyanide, etc. Okay, we can draw Lewis dot structures for these polyatomic ions. The procedure is the same like we did for the neutral atoms, but we have an additional step. We have to realize first the polyatomic ion, whether it's positive or negative, whether it's a cation or an anion, because that information tells us what we need to do with respect to electrons, okay? And so if it's a negative or an anion, we're gonna need to add electrons to it. And so whatever charge it is, we add that number. So if it's a -1 charge, then we add 1, -2, add 2, etc. Okay? If it's a cation, polyatomic ion, this is only for the polyatomic ions now, not for the neutral compounds that we just did earlier. We're going to subtract an electron. Okay? Now, either way, we're going to have a number that is divisible by 2. Because you'll see right away that some of these polyatomic ions, when you add up the valence electrons, you end up with an odd number. So that should be a flag. Wait a minute, I got an odd number. I can't divide that by 2. Okay, I always have a number divisible by 2. And so then you go back and check, okay, is it cation or anion? And that's where you decide whether you're going to add or subtract the number. Okay. Once we figure out the number of valence electrons we have to work with, the fact that they're polyatomic ions, what we do is we put a bracket, not a parentheses, but a bracket around the whole molecule. And then we put the charge of that polyatomic ion on the top right corner. Okay. All right, for example, let's do the first cation. And this is the ammonium ion that was found in the polyatomic ion table. I'll go to that real quick so we can see. Right here on the left, this is called the ammonium ion, which, by the way, these polyatomic ions, that is their name. If we don't change the name of these species. We don't say, nitrogen hydride or anything like that. It is called ammonium, and that's true also for the anions, nitrate, nitrite, etc. That's their given name. So we add up the valence electrons, okay? We got 1 nitrogen that brings in 5 valence electrons and 4 for the hydrogen, okay? Now, if we were to stop there and add the 5 and the 4, guess what? We end up with 9, which is a flag to tell you, uh-oh, we're missing something here. The fact that it is a positive charge, we subtract 1 from the total number that we add up. Okay, so that's one way to remember. If it's a positive cation, I subtract 1. All right, so now I have 8 valence electrons to work with. The nitrogen is a central atom, and so we can very quickly put nitrogen and then bond the hydrogens around it. which is what we did. And we still have 4 pairs around the nitrogen. Where we at? So notice that the nitrogen octet, there's 8 valence electrons around it. And then for each hydrogen, the duet. So the hydrogen and the nitrogen are happy. We still have 4 pairs that we had to work with. We didn't add anything or lose anything. And then because it is a polyatomic ion, we add the bracket around the whole molecule, okay, both sides. And then we add the charge for that polyatomic ion on the outside of the bracket, top right corner. Okay, so that is the proper way to write the structure for the polyatomic ion. Now, can we use the general formula? Sure we can, because it would tell us the geometry. Okay, our general formula here would be A, B, subscript 4. Okay, there's no lone pairs on nitrogen, but there's 4 hydrogens. So with that information, we can go back to the shapes table and look for AB4, which is our standard tetrahedral configuration or name of the shape. Okay, so there you can see where the nitrogen's in the middle, and then the 4 spheres around it representing the hydrogen. And its bond angle here would be 109.5. Okay, that is the optimum configuration that when you have a tetrahedral position, because remember that each bond there represents electrons. Okay, we got 8 electrons around there. And they're negative charged. And being negative charge, though we draw as a line to show what's there, we get a thing 3-dimensional, it's a pretty big area. And so these electrons are going to repel all the other electrons. So in this configuration is the optimum configuration that the molecule sets itself in. So it gives me the optimum repulsion from all the bonds and all the electrons around the central atom. Okay. Now, some other examples. Okay, here's obviously we haven't talked about what these polyatomic ions are, but that's okay. We can still work it through. Notice that all 3 of them are negative charged. They're the anions. So we got to add a electron count depending on the charge. So the first one is bromine, and then you got 3 oxygens bonded around. So what we do, same step. Bromine is in the first 7th group, 7 valence electrons. Okay, oxygen is in group 6, and there's 3 of them, so it brings 18. And then there's a negative charge. We need to add 1 electron. Okay, now that gives us a total of 26 electrons or 13 pairs to work with. The fact that bromine is a central atom and there's 3 oxygens bonded around it, we can very quickly draw the bromine structure and put 3 oxygens around it, like so. And then that takes care of 1, 2, 3 pairs. So we have 10 pairs to work with. And then we just go around putting the 10 pair. And we end up with 1 pair on the central atom. Okay? Which is this case a bromine. We go double check your numbers. We still have 13 pair. We've done nothing to lose any of them. We have a lone pair in the central atom. Okay, and so again we can do the configuration, or not do the configuration, find its shape by figuring out the general formula that we have A, we have A, and then 3 B's, and we also have 1 E. That is a central, we got a lone pair on the central atom. Now, the fact that it's got a negative charge is a polyatomic ion. The molecule itself is polar automatically just because it's a polyatomic ion. But the bonds in there, you can still answer the questions whether it's a polar bond or not, and yes, they are. Okay. But the molecule itself, all ions are just by the nature of the beast, the fact that they got a charge, they are polar. So AB3E is our general formula. We go to the shapes table and we come up with AB3E, same right there. Name of the shape is trigonopyramid, and that bond angle is much less than 109.5. Again, because the lone pair on the central atom takes up more space, squishing all the other things that are bonded to the central atom further down. And therefore, that angle that one would think and predict to be at 109 left the tetrahedral is actually less than 109.5. Okay. Now, the next one, this is a sulfate, called the sulfate. Sulfur is in group 6. Okay, so it brings 6 valence electrons. Oxygen brings in a total of 24 because there are 4 oxygens and they're belonging to group 6. And then it's got a negative 2 charge. So we gotta add 2 valence electrons. Okay, so that gives us a total of 32 valence electrons. Now, knowing that sulfur is a central atom and there's 4 oxygens bonded around it, again, we can quickly draw it with the 4 oxygens around it. And the bond that takes care of 4 pair, which means we've got 12 pair to work with. And we simply have to put those 12 pair around the oxygens because we can't put any more in the sulfur because the sulfur has this octet fulfilled. Here, check the octet for everybody. Everybody has 8 valence electrons. And so the octet is fulfilled for all the atoms. And there we get the general formula. This one would be simply an AB4, which would be tetrahedral. The bond angle there would be 109.5. Okay. And finally, this one, the cyanide, this is called cyanide. 1 carbon brings in 4, nitrogen brings in 5, and then we have 1 electron to add because it's a negative charge, which gives us 10 valence electrons per 5 pair. Here, there's really no central atom because there's 2 atoms, that's it. So you just start putting the electrons around all the atoms, and then if you're short, which you would be short, you start creating, like we did with the HCN, you create a triple bond. In this case, a triple bond is created between a carbon and hydrogen. And we still have 5 pair all the way around. 3 of them are bonded, and the other pair are on the other atoms. Okay, then we put the bracket with the negative charge to show that it is a polyatomic ion. This would automatically be a linear geometry because there's only 2 atoms bonded together. Which is what I was talking about, the lone pairs, how they occupy space because they repel each other and when they're on the central atom, which is basically what this model talks about. They call it the valence shell electron pair repulsion, or the VSEPR. Basically, it just says that electrons that are not bonded are going to occupy more space. And by occupying more space, they're going to affect the bonds on the other bonds on their molecule. Okay, so tetrahedral configuration, whenever I remove something and make that a lone pair, that shoves the rest of them down and decreases that bond angle from 109.5 to be less than 109.3. Okay, I talked already about the been using the ABE general equation. A is the central atom, B is the outer atom, and E is on is a lone pair on the central atom, okay? Now we have this one, the linear, all diatomic compounds or ions are just going to be linear with respect to their shape. So all the diatomic ones, the CN, the cyanide, whenever you have two atoms, that's it, you have a linear configuration, okay? Now, when you have also AB, which is could be just two atoms, or the AB2 shape, which is also linear. The example we had earlier was carbon dioxide, okay? It's an AB2, so it's AB, AB2 are linear. Now, when you have an AB3, in which you have a central atom, and then you have three moieties bonded around it, you have what is called the trigonoplanar, okay? And there's 180 degrees all the way around the central atom with respect to the moieties that are bonded to the central atom. This, for example, is the structure for formaldehyde. You may be familiar with it. It's a preservative. Tetrahedral is what I talked about earlier. That is the most common configuration or shape that we find in nature, where you have the central atom and then four moieties bonded around it. Okay, this one here is this example is called methane gas, where you got the central atom of carbon represented three-dimensionally there on your right, represented in black, and then the gray is the gray or the white is represents the hydrogen. Now the AB2E is the bent configuration, okay? Now you might think SO2 would be very similar to CO2, but remember, carbon is in group 4 and sulfur is in group 6. So sulfur will bring in more electrons into the structure. And if you go through the electron dot structure, you end up with that moiety there on the left, okay, where that bond angle is much less than 120. Okay, like this is 120, but because there's a lone pair on that central atom again, in this case sulfur, it occupies a lot more space and it squishes that bond angle between the oxygens to be much less than 120. Okay, let me rehash for a second. Remember, we did the carbon dioxide, and I talked to you about how the polarity of these bonds cancel out. Okay, because they're going in opposite directions. Because they have the same magnitude, but they're going in different directions. Okay, the one on the left is going in the negative direction, the one on the right is going in the positive direction. The result is they cancel each other out. Okay. With respect to this one here, they also have polar bonds, but this one here, because of the lone pair, is going in the downward direction, downward toward the right, and this one's going downward toward the left. Now, how do I know that I drew the arrows in the right direction? Well, if you look at the periodic table, you'll see that oxygen is much closer to fluorine than sulfur. Oxygen's in the same period. Sulfur is the next period down. So the polarity of oxygen is greater. So oxygens are pulling the electron density away from the sulfur, okay, and making this a polar bond. However, they don't cancel out because that lone pair causes them to go in different directions. And therefore, the result is that you have a polar molecule, polar bonds, polar molecule. Carbon dioxide had polar bonds, non-polar molecule, because the polar bonds canceled out in carbon dioxide. And then we have this example of ammonia, which is called trigonopyramid. where you have a lone pair on the central atom, which I said you can always bet on when you get a lone pair in the central atom, you can have a polar molecule. We have a lone pair in the central atom, that's polar. Lone pair in the central atom, we have a polar molecule, okay? Here we have ammonia with the lone pair in the central atom, and therefore pushing the bond angle between the hydrogens to be much less than 109.5. And then we have an example here for a bent configuration, the AB2E2. Classic example is water, where you have oxygen has two lone pair. So that bond angle, it says less than 109, should be much less than 109 because those two lone pairs on the oxygen really take up a lot of space. Okay. And hence water is extremely polar. Okay. Very polar. So with respect to this section, I'd be able to draw dot structures, Lewis dot structures, and from the Lewis dot structures, determine the shape and the bond angles like we just did. So you may want to try pH 3 and ozone, very good challenge. Okay. Try those, and you can send me an email if you have any questions, if you can come up with any answer. Okay, but pH 3 is very similar to ammonia, FYI. Okay, so I've introduced to you the concept of bond polarity and how it's, how we determine whether a bond is polar. And it has to do with electronegativity, which is what we talked about last chapter. Okay, so when a covalent bond, and we're only dealing with covalent bonds. So we have ionic bonds, which deal with the electrostatic attraction of two ions with a full-fledged charge. Ionic compounds have a full-fledged charge in them. And there's no sharing, no physical sharing of electrons. It's just an attraction like two magnets because of the positive and negative. With covalent bonds, it's not the case. There's an actual bond and there's sharing of electrons between two atoms. Okay? When there's equal sharing, we have what I've stated before, what we call a non-polar bond. Okay? The term polar sometimes confuses people, but if you think about it, there's a lot of examples around us that you're familiar with. The Earth, for example, is polar. We get a North Pole and a South Pole. Okay, batteries is another example of something that's polar because you've got a positive end and a negative end. Okay. All right. So when that covalent bond, when there's unequal sharing, then we create a polar bond. Just like the magnets like a magnet, we got a polar bond. We got a north and a south, so to speak. Okay. Now, we talked about electronegativity a while back, and that is the affinity of an atom to attract electrons onto itself when it's bonded with something else. Okay. And fluorine is the most electronegative. So that's our benchmark to determine who's more negative when we want to compare another different combination. Okay, so whenever you see fluorine involved in a bond, without question, that's the most electronegative atom, and therefore the polarity is greater for the atom. And for fluoride, and fluoride is pulling the electrons onto itself very strongly. That's why they use fluorinated toothpaste. The idea is it's incorporated into your teeth, makes for strong bonds in your teeth, strong attractions and so forth, and strengthening your teeth. So the theory says, okay? All right, so we know that noble gases do not have an electronegativity because their octets full, they're happy. Our general trend on far right, top right corner, that's what fluorine occupies. So that's our benchmark. Okay. all of the diatomic molecules that we talked about, have no fear of ice cold beverage, those are non-polar bonds. Okay? And included on that is one more, and that is a carbon-hydrogen bond. It is treated as a non-polar bond. All right, so one concept that sometimes people have a hard time with is determining if a bond is polar or not. And the rule of thumb is this: if it's not diatomic and if it's not carbon-hydrogen, then it's polar. Quite simple. Okay, so if it's not diatomic and it's not a carbon-hydrogen bond, you got a polar bond. Once you got that worked out, the next question would be, okay, which atom is more electronegative? And then you refer to the periodic table to determine where they're at in relationship to chlorine. So carbon, oxygen, automatically polar bond. Hydrogen chloride and chloride, polar bond. Sulfur and fluoride, definitely a polar bond. Silicon and nitrogen. Notice that they're all different elements bonded together. So they're automatic by default are polar covalent bonds. Okay. Now, what we use is called the polarity arrow, and this lowercase delta, this symbol that you see here. Okay, that is the lowercase Greek symbol delta, which basically we use it to say it's partial positive. Bear in mind, the ions, like sodium ion, had a full-fledged positive, and the chloride, for example, had a full-fledged negative. Okay. The polar bonds here, the covalent polar bonds here, have a partial. Okay, they didn't take the electron density away. All they did was pull the majority of it, a lot of it toward itself. And so what we use an arrow to designate in which direction the pull is going to. And so if you look at the bottom example, bottom left corner, you see carbon fluoride. Well, fluoride is the most polar atom there is. And so fluoride will be pulling the electron density onto itself. And in doing that, it creates a partial negative area on fluoride. And hence we put the partial negative over the fluoride. The result is on the other side of carbon, by it pulling the electron density away from carbon, it's made it a partial positive area, okay? And we can draw the arrow from left to right, where the arrow is pointing toward the fluoride, and then on the left side, you got a little plus on the arrow there that represents the partial positive. So that arrow goes from left to right. This is what happens. You can actually create a polar environment. If you take a balloon, for example, and you rub it on your head, and you put it on your chest, it sticks, doesn't it? Yeah. I mean, you tried it. Have you ever tried it? If you haven't tried it, try it. Get a balloon, rub it on your head, and put it on your chest, and it sticks for a short period of time. Well, what's happening there is by rubbing that balloon on your head, you're transferring electrons onto the surface of the balloon. The electrons have a negative charge, as you all know. Well, as I bring it to my chest, on my chest, outside my shirt and everything, there's an electron cloud down in the atomic scale. I got nothing but electrons down there. What happens is, as I bring the balloon closer to my shirt, those electrons on my shirt and the electrons on the balloon repel. And so what happens is on my shirt, they kind of go into me, if you will, creating a partial positive area on my shirt. And now the balloon has a partial negative, So the balloon now attracts and they hold on to each other because of the partial positive on the shirt and the partial negative on my shirt, on the balloon. And so the balloon sticks to my chest for a short period of time until such time the electrons equilibrate, and then everything goes back to normal and the balloon falls off. Okay. Now this has a big factor. The polarity has a big factor on how molecules behave with each other. Because if we look at another molecule of, say, carbon fluoride, let's say I just put it there. Okay. Well, that carbon has a partial positive on the blue molecule, the blue bond I wrote. So there's going to be an interaction between the molecules right here. There's an interaction that's occurring between the left CF bond and the right CF bond, because the right CF bond has now, the carbon has a partial positive and the fluoride actually has a partial negative. And depending on the strength of that interaction, that affects things like boiling point. So every time we heat something, we get it to boil like water. By putting energy into the water, we're breaking up the interaction of the water molecules they have with each other. And it takes 100 degrees Celsius to break that interaction to get that water to boil. So all the energy that goes in is breaking the interaction between the molecules, which is related to the polarity within the molecules and how much of a polar bond they have. And that's why water takes 100 degrees Celsius, but alcohol, good old-fashioned drinking alcohol, boils at about 78 degrees Celsius. So its interaction with other molecules is much less. It doesn't take much energy to get that thing to boil. And acetone, like our nail polish remover, even less. Boiling point's even lower. Acetone is very volatile. Okay. All right, so it's all related, the properties of compounds is all related to the polarity of the bonds and the strength of the bonds and the type of interaction they have with each other, which is what we're going to be talking about as we progress through the chapter. So this stuff doesn't go away, it continues with the other chapters. All right, let me clear all this. Now, if you look at the central molecule, the OH, oxygen is a lot more electronegative, so we draw the arrow from right to left. Oxygen has a partial negative, and hydrogen has a partial positive. That polarity, as an organic chemist, back in the day when I was synthesizing compounds, when we were designing to make new compounds and get things to react, we always look for it. That's where all the action happens. That's where all reactions occur, are areas that have polar bonds. Otherwise, areas that don't have polar bonds are very difficult to react at a certain area. But we tap into the polarity of a molecule so we can go in there and redesign it and make new compounds. Okay. Now the phosphorus chloride, also, again, polar bond, but the arrow we draw from left to right because the chloride is a lot more electronegative than the phosphorus. Now we know about noble gases. You know, nothing's going to happen. So they're not going to react. Their octet's full, so we're good with that. Now here they're asking you to write the delta notation, which is the partial positive and the partial negative, and the polarity arrow, which is the arrow with a little plus sign at the end. They're asking you to draw it here. And so we have carbon, oxygen. Obviously, we've got a polar bond to different molecules. Okay. We check to see who's more electronegative. Oxygen's a lot more electronegative, so we draw the arrow, in this case, from left to right. And we put the partial negative on the oxygen. Nitrogen fluoride, no doubt, fluoride is the most electronegative. So therefore, the electron density or the arrow is going toward the fluoride with a big partial negative on the fluoride itself. Oxygen and hydrogen, we just talked about that. In this case, we draw the arrow from right to left, okay? Now, they may draw it like this, O, and then followed by H, but they can also draw it H-O, okay? Either way, it could be shown, but it's up to you to draw the arrow in the right direction. Carbon chloride definitely have a polar bond. Chloride being a lot more electronegative than carbon, therefore the arrow goes from right to left. Now, when it comes to hydrogen and carbon, as I stated earlier, with respect to the diatomics, the electronegativity of hydrogen and carbon is essentially the same. So it's a nonpolar bond. So there would not be a delta notation or a polarity arrow for a carbon-hydrogen bond. Okay. Question here was how many bonds are ionic, and if so, which ones are polar or non-polar? Well, based on the definition of the two compounds, ionic versus covalent or molecular, ionic bonds require a metal and a non-metal, and so the only one here is a sodium chloride, okay? Which means that the other ones must be polar, or covalent, excuse me, okay? Now to determine the subset of covalent compounds, whether polar or non-polar, we look at what's there. We got two bromines bonded together. They're both the same. Electronegativity is equal. Therefore, it's non-polar. The PF obviously is polar, two different elements. And the FBr is also polar. Okay? Two different elements interacting together. Okay, so, the concept of polarity is very crucial. We use it over and over and over again. And when we get into what's called molecular forces, intermolecular forces, polarity is what comes into play to help us define the type of intermolecular forces which are based on the type of polar bond or non-polar bond, okay? All right, so here's to ask you, determine ionic, the polar, non-polar bonds. Like, well, as we stated earlier, ionic bonds, metal and non-metal, okay? So that's definitely ionic. It has nothing to do with being polar or non-polar. By default, ionic compounds are polar molecules. They readily dissolve in water. Okay, some dissolve strongly, some dissolve not so much, but they still dissolve. HCl, definitely a polar bond, two different elements. So we have a polar covalent bond. H and H, it's a covalent bond, but they're both the same, so it's a non-polar covalent bond. Chloride and the carbon, definitely a covalent bond, and it's polar. Two dissimilar atoms, okay? Carbon and hydrogen, covalent bond, but the electronegativity, again, between the two is the same, so it is classified as a non-polar covalent bond. Carbon and oxygen, okay? Two same elements, definitely a covalent bond, but non-polar. It's one of the diatomic compounds. And then potassium and oxygen, in this case oxide, definitely ionic. You've got a metal and a non-metal. And then finally, the last entry, no question about it, we got fluoride sitting there. Unless it's fluoride bonded to fluoride, then there will be non-polar. But it's fluoride bonded to something else. And we have a polar covalent bond. Okay. So, as I stated before, when I was talking about polar bonds, when within the molecule, if all of the bonds are nonpolar, then you can say that I have a nonpolar molecule. Okay? When the polar bonds do not cancel out, you have a polar molecule. So in general, polar bonds in a molecule give you a polar molecule unless they cancel out like they do with carbon dioxide, okay? Or in the tetrahedral position. And if they cancel out, even though they have polar bonds, they overall are a non-polar molecule. See, once we determine that, then we can make predictions and say, okay, then we know that the first example there, sulfur dioxide, will be a lot more soluble in water than carbon dioxide. And carbon dioxide being nonpolar, it'd be a lot more soluble in the oil base in a nonpolar solvent than sulfur dioxide. Now, here we have some examples where we have methane, CH4. We talked about that earlier. It's all nonpolar bonds, so it's polar. It is a nonpolar molecule. Now, if you do phosphorus trichloride, chloride right under is in group 5. And you can always guess, not guess, but determine, deduce that being in group 5, which is where nitrogen is, and there's only 3 moieties bonded there, you're always going to end up with a lone pair in the central atom, okay? And that means just the fact that it's got a lone pair in the central atom, in this case phosphorus, you've got a polar compound. Then you add that the fact that you got phosphorus and chloride bonds, which are 3 polar bonds, okay? And they don't cancel each other out because that lone pair sitting there on the phosphorus. Carbon dioxide, we talked about that, polar bonds, but they cancel each other out. So overall non-polar, okay? So we did water already, we did ammonia, and we did, yeah, we did those 2, so. All right. Guess what? Congratulations, you're done with chapter 7, excuse me. Okay. Nicholas, you have any questions?
I don't think so. No, I think I'm all good.
Okay. Tell you what, let's very quickly, give me 5 minutes. I got to do a quick thing here to my system, and I'll be right back, okay?
Okay.
Okay, I'm back. I was getting a lot of feedback on my sound. I was checking my sound card. All right, well, let's continue with chapter 8. All right, chapter 8, fairly short chapter. I'll knock this out also here real quick. But it deals with nomenclature, which basically name the compound. So in this chapter, what happens is we start naming compounds, or we're given the formula and we're asked to name the compound, or we're given the name and asked to give the formula, back and forth. So this is in line with that nomenclature exam that the department requires that students pass. And if you notice, what I do is I put a 0 in that assignment to give you an idea what effect. It's only 10% of your overall grade. And when I put the 0 in, a lot of people send me an email, what happened to my grade? Well, not everyone has done the nomenclature yet. So it just gives you an idea of, by putting a 0, what your grade truly is if you don't pass this part. Okay, and it could have an effect, especially if you're on the border. All right, so I mentioned at length about the naming of the atoms. Okay, we talked about simple atoms. We just give them the names. Okay, we mentioned before that. Be familiar with the first 20 name-wise, but then we added a couple more, a few more. We have Ba, which is barium. We got Co, which is cobalt. I, which is iodine. Cu, which is copper. Fe is iron. Pb is lead. Hg is mercury, and Ag is silver. Au is gold. That gets confused. People could get too confused, Ag and Au. Au is gold. Zn is zinc. Sn, its official name is stannous, but the most common name they give it is tin, Tin. And we got strontium, Sr. And I is nickel, Br is bromine, Cr is chromate, manganese is Mn, which people confuse with Mg, which is magnesium, okay? And then Cd is cadmium. Those are some names you may want to be familiar with. Now, I talked at length about ionic compound. The ionic compound is defined as a combination of the metal and the non-metal, okay? Whereas covalent compounds is a combination of nonmetals only. We also call it molecular compounds. Then we have the monatomic ions, where we got the sodium ion, the chloride ion. Now, when we, with respect to the name, let me go back to the periodic table real quick. With respect to the names of the nonmetals, they're the only ones that change the name. And so if we look at, here, make sure I got the right one. And I'm just going to do nitrogen and phosphorus. When nitrogen and phosphorus become ions, and they're going to pick up 3 electrons having a -3 charge, nitrogen's name becomes nitride. Phosphorus name now becomes phosphide, okay? And then we have, we can do oxygen to selenium. Oxygen, its name on all 3 of these highlighted will gain 2 electrons because they're in group 6. And when they become ionic, their name changes from oxygen to oxide, sulfur to sulfide, selenium to selenite, okay? The halogens, which I'm just going to do the fluoride down to the iodine, the name again changes from fluorine to fluoride, chlorine to chloride, bromine to bromide, and iodine to iodide. So only the nonmetals change the name. And if I were to put sodium and chloride together, chlorine to make a ionic compound, sodium will remain the name sodium. And obviously the chlorine becomes chloride. All right, so now we have the polyatomic ions, and those are again in the table of the periodic table on the bottom left corner. Okay, they have their own special name which doesn't change. And so you can see there's only one cation there, the ammonium that we talked about earlier. All the rest of them have a negative charge. Okay, and they come together as a group, as a packet. We don't change it. So if I ever need to have more than one nitrate, for example, we're going to put a parenthesis around the whole unit, and then put a subscript outside the parentheses with, say, if I need 2, I put 2. If I need 3, I put 3. But we don't change the structure or the formula of the polyatomic ions, nor do we change the name. This has the name nitrite. Now, let me show you something else real quick. We had we had nitrogen, for example. That's the element. When it becomes the ion, it becomes nitride. That's the one with the N3. Now, if we take nitrogen and we add 3 oxygens to the central atom, it becomes that polyatomic ion. And that is called nitrite, excuse me. Now, if that's with 3 oxygens bonded to the nitrogen, but if there's only 2, we have an additional one, which we call nitrite. Okay? And so the naming of the anions, with specifically with nitrogen, tells you, if you have the name, which one you're working with. Because sometimes you might say, write the formula for sodium nitrate. And people inadvertently mistake the 8 for the IDE and simply write the nitrogen. Okay, that's why it's important to distinguish between the IDE, the ATE, and the ITE. The same is true for sulfur. We got sulfur, sulfide, sulfate, and sulfite. Okay, so naming is naming is important. Okay, we have the polyatomic ion. So oxidation states. Now you might hear me at times say, what is the charge? Or I would say, what is the oxidation state? Technically, when we get to covalent compounds, they don't really have a charge. So the term oxidation state, remember they have, with covalent bonds, they have a partial charge. And so technically what we should be using is the term oxidation state, because the oxidation state will tell you the charge, if you will, be it an ionic compound or be it a covalent compound. So I may interchange the term oxidation state and charge. Okay, we all know that the elements all have a 0 charge because they have an equal number of protons and equal number of electrons. Okay, when they are in the elemental state. Once they lose electrons or gain electrons, they become ions, either a cation or an anion. Okay. Now, there are 16 elements that have a constant or a fixed charge. So if you have your periodic table, which you may want to mark these. Okay. There's 16, I call them the sweet 16. Now, everybody on group 1, starting with lithium, down the column, all of those, when they become ionic, will always have a +1 charge 100% of the time. their charge will not vary. And I'll explain that, what I mean by vary in a minute. The ones in group 2, starting with beryllium down to Ra, all will always have a +2 charge. Group 1 has a 1 valence electron, group 2 has 2 valence electrons. So those 12 will have a fixed charge 100% of the time. Then we add 4 more, starting with aluminum, number 13. Aluminum will always have a +3 charge. Zinc, right catty corner to aluminum, will always have a +2 charge. And then silver, Ag, number 47, will always have a +1 charge. And then move over to the right, ruthenium always has a +2 charge. Okay, so these are called the sweet 16. Okay, they have a fixed charge. What that means that all the other metals that we had left over have a variable charge. And it's difficult to tell you 100% of the time which one is going to be the case. It depends on the reaction conditions. And so we have to distinguish between them. For example, copper, in that example I gave up here, Cu, there's two types of ions. It could have a +2 or it can have a +1 charge. And to distinguish between the two, we use Roman numerals, much like the Roman numerals up on top of the periodic table, but in this case, the Roman numerals are related to the metal. Okay, so if I wanted to write out copper 2 because I want to use copper +2 charge, I would say write copper and then parentheses, Roman numeral 2 and parentheses, versus copper, Roman numeral 1. Okay, two distinct different compounds or ions. Copper 2 has a blue color. Copper 1 has a kind of a greenish tinge color. Totally different properties and totally different, just different properties. But we need to distinguish it. And the old way of naming these, we used to call them cupric and cuprous, and it was very ambiguous. So everybody in the international community, there is an international community with respect to naming compounds, decided we're going to use Roman numerals to distinguish the two. So when you see the name, a Roman numeral in a name, that Roman numeral pertains to the oxidation state of the metal that you're given. Okay? All right, so let's head back. Okay, we know about metals. All metals lose electrons. We talked about group 1, group 2, group 3, and their respective charge that they have. Okay, I threw in the zinc and the cadmium, always have a +2. Okay. Silver always a +1. That means that all the other metals can vary from an oxidation state of a +1 all the way to a +9. Okay. It depends on the conditions. And here are some examples of other metals that are not part of the 16, okay, that we have to use Roman numerals. That means for the 16, when we name them and we write their name out, there should be no Roman numerals because the oxidation state is exact, it's constant, okay? So only for all the other metals that we use Roman numerals. So we have copper 1, copper 2. Iron exists in two ions. There's an iron 3 and an iron 2. Lead could be a +4, and a variety of different ions. Okay, so we use Roman numerals to tell us the oxidation state of the non-16. Now, nonmetals we know gain electrons, okay? And so let me go back to the periodic table. for a second. And I just mentioned earlier about the name, but the name changed. But we know going back here that in group 5, both the nitride and the phosphide will always have a -3. In group 6, we'll always have the -2 and -1 for group 7. And so for the single element, so if it's nitride, always a -3, oxide -2, chloride -1. So what does that mean? Okay, how does that help you with respect to the other metals that you may not know what their oxidation state is? Well, we know that when we put molecules together to write formulas, we have to put enough cations plus enough anions equals 0. And so if I have a formula like CuCl, okay, the question is, okay, what charge does that copper have? Well, I just stated it could be either copper 2 or copper 1, but the way I wrote it, what is it that I know? You're always going to know the oxidation state of either the cation or the anion. Here I don't know the oxidation state of the copper, but I do know the oxidation state of the chloride. The chloride is -1. And in order for me to write it with CuCl, that means that I must be using copper 1. Chloride. Okay? Because the chloride is a -1, and I have only one of them, which means I gotta have, that must be copper 1. Compared to, say, CuCl2, well, that has to be copper 2 chloride, because I have 2 chlorides, which each have a -1. So that means that copper must be a copper 2. Okay. And so, like I said, the general formula for the cations is this, that and then the number of cations plus the number of anions will equal the overall charge of the compound. And this is the very good very good general formula, because majority of the compounds you have, the overall charge of the molecule of the compound is 0. Okay, and so you can easily, if you don't know what the charge is in the cation, you always will know what the anion is, or vice versa. Okay, and you can solve for what's missing. And I said the overall charge because you can apply this equation to those polyatomic ions, because those polyatomic ions have the overall charge of, let's say, the nitrate. The nitrate has a negative charge. Okay, so I don't know what the nitrogen is, but I know what the oxygen is at -2 for the nitrate. So I can calculate the overall charge for that nitrogen as a nitrate polyatomic ion. You'll see some of the homeworks where you have a charge on the ion and they're asking you to figure out the charge. And using this equation, you can figure it out for any compound or any type of molecule they give you. Okay. So this is a rehash of what I just explained. -3, -2, -1. Obviously, noble gases have now octet full. Nothing's going to happen. Okay. Now, when we're dealing with ionic compounds right now, we're going to get to covalent compounds. And thing to remember, that ionic compounds are made of ions, and ions have a charge. And for this example, I said the sum of the charges equals 0, or the overall charge of the compound. Okay. The polyatomic ions, be familiar with them. We do use them quite a bit. Okay. And as I repeated what I said earlier, if we need more than one, we keep them together and we put parentheses around them. Okay. And we'll do some of those examples in a second. Now, if we take, they say here, combine sodium and nitrogen. So right now they're just giving you the elements. So what you're going to do first is the first thing to do is to convert those elements into their respective ions. We know that sodium is a +1 because it's a group 1. And we know nitrogen is a -3. It's nitride now, okay? And so now I got them in ionic form, keeping in mind that I got to put them together with enough of each to equal 0. So I need 3 sodiums to cancel out the -3 of the nitride. Okay. So my formula written would be Na subscript 3. That tells me that I have 3 sodiums, each one with a +1, to counter the -3 of the nitride. So its name will be called simply sodium nitride. Write that. Sodium nitride would be the name. In this case, we went from formula to name. But one should be able to go backwards and go from name back to formula. Okay? Let's try this one. All right. So first thing we're going to do, you're given the elements, you break them down into ions. Okay, so sodium, like we did the previous example, we know has a +1. And sulfur is a -2. It's in group 6 ions. All right, so now, once I figure out the ions, now I got to figure out how many of each I need to cancel things out. And based on the charges, I need 2 sodiums to cancel out the sulfide. So that 2 I wrote becomes the subscript for the sodium. So that becomes sodium subscript 2 sulfide. Okay. Magnesium and oxygen. Yeah. Take a systematic approach, break them down to the ions. Magnesium's in group 2, so it's going to be a +2 charge on the magnesium. And oxygen would be a -2, okay, as an ion. And so those are the 2 ions I need to put together. Now, luckily, they both have equal charges and opposite magnitude, so I just simply have to put them 1 to 1. Give me that formula. And so what I did here, the top one was sodium sulfide. And magnesium oxide. The name. Okay. Here, you got potassium and phosphorus. Put them into ionic form. Okay. We know the phosphide is group 5. And so write them in ionic form first. And make sure that you got them, you will put them together in the right number. And the phosphide would be a -3. It's just like the nitride. That's phosphide. And so I'm going to need 3 potassiums. Okay. And so I have K3, subscript 3P, which would be potassium phosphide. Eventually, you know, I like I said, I recommend first break it down into the ions and then put them together and just go through a systematic approach of writing them out. So till you become familiar with them. Eventually, you get to the point where you look at it and you'll know automatically the formula. But like anything else, it takes a little practice. Okay. This one's a little more challenging, but not undoable. Same procedure, break them into the ions first. Okay. We got calcium, which is a +2. It's a +2. And then we got nitrogen with a -3. Okay. Well, the previous examples are pretty straightforward, right? You can add 2 of 1 or whatever we need, 3 of 1. But here we got a little bit of a problem somewhat because we got a +2 and a -3, and we got to put them together such that they cancel each other out. So you might give this some thought. Say, well, think about this for a moment. What do you do when you want to add Roman numerals, fractions like 1/4 plus 1/5? How do you handle adding those 2 fractions?
Sorry, what were the 2 fractions again?
Yeah, 1/4 plus 1/5. What would you do to add those 2 fractions?
You have to find the common denominator, which would be 20.
Exactly. And here I got to put together a +2 and a -3. So I got to find a common denominator. So what do you think the common denominator would be here?
6.
I got to put enough positives together with enough negatives so they cancel each other out.
Would it not be 6?
You sure would.
Oh, okay.
Yeah, it's 6. Because I would need 3 calciums, right? Which gives me a total of +6. And I would need 2 nitrides. Wouldn't that give me a total of -6? And so now I've found how many of each I need to cancel out the total charge. And so when I get numbers that are not, I can't put either, 2 to 1 or 3 to 1. I got to find a common number, a common charge. In this case, like in the fractions, the common denominator, if you will, for lack of a better word here, is 6. So I got to add enough of nitrogen to give me a -6, and enough calcium to give me +6. And so now my formula is CH3N2. Okay. And there's a little bit of a trend if you really think about it. If you look at that formula. Now, if we look at the subscript 2 for the nitride, wasn't that the charge for the cation plus 2, right? And if we look at the subscript for the calcium, wasn't that the charge for the anion? So we basically cross it over, and that automatically puts you in the right number of ratios that you need. But if you don't see it, then break it down, find a common charge for both the cation and anion, put a number up front for each ion, and that becomes a subscript that is used in the molecule. Oh, erased everything. All right, so aluminum chloride, break it down. We got aluminum, which is a +3, and the chloride, which is a -1, excuse me. We need 3 chlorides to cancel the +3 of aluminum, and we end up with that formula, which is called aluminum chloride. Now, I had the names earlier, but we had sodium sulfide, magnesium oxide, potassium phosphide, calcium nitride, and now aluminum chloride. Notice that I didn't use the Roman numerals. Why? Because all the cations here, all the metals were part of the 16, okay? Part of the 16, so I did not need to use Roman numerals. So you don't use Roman numerals for the 16. If you write the Roman numerals for the 16, it's incorrect. All right, they have a constant charge. Same is true for this one. We got zinc that always has a +2, and iodide, which becomes a -1 each one, and when it becomes an ion, that means I need 2 negatives, 2 iodides for every zinc +2. So my formula now is zinc iodide. Notice the name change. Went from iodine to iodide. Excuse me. Now, here comes the Roman numerals. Obviously, copper is not part of the 16, so we had to tell you, okay, which ion am I working with? And so that Roman numeral is telling you that you are working with Cu +2. And the ion is oxide, and we know it's in group 6, so it has a -2 charge. And so that's a baddie. That's supposed to be a plus, not an equal to. Okay. Okay. And so that's a +2. Clear that. Confusion. I pushed the wrong number on my keyboard. Cu +2. And oxide is a -2. And so here I can put these together as a 1-to-1 because I got a +2 and a -2. So my formula is simply CuO. My name, if I needed to write this out correctly, would be copper, Roman numeral 2, oxide. Okay. And notice here we've been doing specific examples, but you know what? You probably already have access to 300-400 different compounds. Because even though we use sodium up in this case with sulfide, you can hook it up with oxide, phosphide, nitride, the chloride, the iodide, or any of the polyatomic ions we talk about. Vice versa, you take magnesiums, you can do that with sulfide, phosphide, nitride, etc. So you're seeing you're building up a library of compounds just by mixing and matching the cation and the anion and putting them together with the right number of each to equal 0. To equal 0 in this case. Okay. This example is Pb, which is lead, Roman numeral 4. They're telling you you're using the +4 ion. Oxygen, like the previous example, has a -2, which tells me I need 2 oxides per every lead 4. So our formula becomes lead, Roman numeral 4, oxide. Okay. So when you put them together, just make sure that they all add up to 0 in this example, unless you're given the charge. You know, for example, what I mean by, let's take nitrate, NO3 -1. Okay, it's just supposed to be a superscript. It's not. working well. Okay. NO3 minus 3. Let me try this, for example. I got a new toy here. Let me see how it works. Okay, somewhat. That's the nitrate ion. Okay. And so I want to figure out this is the central atom. I want to know the oxidation state of nitrogen. Okay. I don't know what it is in this form. So I can write nitrogen plus, all right, I have, well, I won't write it. Each oxide is a -2, correct? And so I have a total of -6. Not coming out very good. Okay. I have a total of a -6 charge, each coming from 3 oxygens. Okay. And the overall charge of the molecule is a -1. Okay. Can I solve for N here? What will be the oxidation number of nitrogen? What do you think?
That's a good question.
Pardon me?
It's not 6, is it? Or
No. Yeah, because I got to move that -6 over to the right. So I add -6 to the left.
oh, it's
Then
5.
Yeah, exactly. So
Okay.
nitrogen under this the nitrogen in the form of nitrate has an oxidation number of +5. And I use that equation where the cation plus the anion, the number of cations plus the, let me restate it, the number of number of cations plus the number of anions equal the overall charge of the molecule. Most of the ones we've been doing right now have been 0. That -1 will be 0. But you can also do polyatomic ions. Okay, just making sure that the overall charge will be equal to, in this case, -1. So yes, as a nitrate, nitrogen has a +5 oxidation number, which means it lost 5 electrons under these conditions. Oh, yeah. All right. So what I'm going to do here, I got to get to an appointment, but I'm going to stop it right here. Let me slide number 10. Yeah, we'll continue next Friday on this chapter and then go on to chapter 10 from there. So other than that, I want to thank you for showing up. I will update your